Good morning and welcome. Today we will focus on how do you build consumer-focused web services, especially consumer-focused content-based web services for millions of customers. And how do you build a robust content store where you can store tens of billions of files which have variety of content type, and how do you store the metadata for this variety of content in a flexible way such that you can find and organize the content for your customers easily. And as your content continues to double at a rapid pace, how do you still provide a consistent customer experience? We'll share with you how we achieved this today. I am Tarlochan Chima, Software Developer Manager for Amazon Cloud Drive Services team. And with me here today is one of our key senior developer, Kevin Christian. Today we will share with you how we built and scaled Amazon Cloud Drive Services to serve millions of consumers leveraging AWS technologies, and how we built a robust content store leveraging S3 and provided unlimited storage to our customers. The goal of this session is to provide some key learnings from our experience and provide you with some effective design patterns and best practices that you can take and apply if you're building highly scalable content-based web services on top of S3. I'll start by providing an overview of what is Amazon Cloud Drive. I'll share with you some of the key challenges we had and some of the design goals we had. And then I'll walk you through the design architecture which helped us achieve the scaling, performance, and the fault tolerance goals we had. And then Kevin will come over and he will get deeper into the content store and share with you how we leveraged S3, where it worked out of the box, and where we faced some challenges and we have to do something more custom. So what is Amazon Cloud Drive? Amazon Cloud Drive is a consumer cloud storage service where customers can store any type of content. Their photos, videos, document, they can back up their devices, any other content they may have. Now, if you mainly want to secure your memories and just want to back up your photos, then there is an unlimited photos subscription plan, which comes with additional 5 GB where you can store any other type of content which is not photos. However, if you really want to take more device backups and really want to push more files, videos, and documents, then there is an unlimited everything subscription plan, which is probably the right plan for you. Now, you can get started for free for 3 months and try them out. If you are an Amazon Prime subscriber, you get the unlimited photos for free. It's a great plan, and if you want to learn more about these, you can go to amazon.com/clouddrive. How do you use Amazon Cloud Drive? We have a web-based app which you can access from all modern browsers on any device, or you can download one of the mobile app on iOS, Android, or Fire OS, and it provides great photo, auto uploading capabilities, and it also provides some great organization and sharing capabilities as well. But if you really want to manage your files and push them from your Mac and PCs, we have file uploader and downloader apps which you can download on Mac or PC. And again, you can go to the website and see what we have out there. So what's in here for developers and partners? Well, we have RESTful APIs and Android and iOS SDKs. These are the same APIs and SDKs which we leverage to build our apps, which I just mentioned. And if you have some great, cool, innovative ideas, you can build apps, reach millions of customers rapidly. And Amazon Cloud Drive is a subscription-based service, so there is no free tier. So if your apps help us reach more customers, and they sign for subscriptions, then there are some great revenue sharing opportunities waiting for you. Again, if you're interested, you can go to the URL at the bottom of the slide. Slowly, we are gaining good momentum, and there are some great third-party partners and developers building some really cool apps. There are files which allows you to manage your photos in a cool, interactive way, and there are some great file management and syncing apps as well. And again, we are relatively new in this space, so if you have some cool, innovative ideas, you can build some apps, help us reach more customers, and there are some great revenue sharing opportunities here for you. So now that you have a good sense of what Amazon Cloud Drive is, here are some of the key challenges we faced. And if you are building a highly scalable, content-based web service, you might be facing some similar challenges, maybe not at the same degree or level, but generally they're pretty same. And really what this comes down to is how do you handle huge volume, variety, and velocity of content, which continues to grow at a rapid pace? And how do you store the related metadata in such a way so that if you get a new content type, you don't have to change your schemas, but still you're able to do indexing such that you can find, organize the content in a meaningful way for your customers. And in our case, we get hundreds of millions of service requests on a daily basis. So how do you log these log all the service requests which are coming your way? And how do you build analytics and some monitoring so you can proactively manage your services? And above all, it's not about how you effectively do this, but how do you efficiently do it so you gain the performance and your cost is lower. Here are some of the key design goals we had, and if you look at this list, it probably looks very familiar. If you're, again, building highly scalable web apps or services, probably you have the same list. And in our case, it came down to really a few things. One was, how do you provide consistently great customer experience as you continue to grow your volume and your user base, as more and more users are coming consecutively and hitting your services? And in our case, there is also, and maybe this is the same case you guys are also dealing with, we have customers who are using different types of mobile devices. They're uploading photos from their phones. They want to experience that from tablets and Mac and PC. So how do you provide near real-time experience to your customers when they're doing this? And again, how do you ensure there is no loss of data? And again, how do you keep the cost low? So let me share with you how we achieved this. And this is a very high-level overview architecture design for Amazon Cloud Drive. The key components in here are, one is our content store, which is built on top of S3. S3 provided us the durability, the reliability, and the performance we needed. And all the related metadata is stored into a metadata store, which is built on top of DynamoDB. And DynamoDB provided us the fast reads and writes for the metadata. It also provided the flexible metadata store we were looking for. Now, for advanced querying capabilities, we have a separate indexing engine as well. Let me share with you what happens on upload and a download such that you get a good sense how all this comes together. So when a customer uses one of our apps and pushes a file through the app will hit our Amazon Cloud Drive service, and the service at that point will put the metadata into the metadata store and put the content in a pending state. At the same time, the content will start uploading into S3, and once the content is fully uploaded, we then mark that content available in our metadata store. At the same time, when it's available, we push the metadata into the Kinesis stream. From there, it's picked up by several SQS workers. There is a SQS worker which pushes the metadata into our indexing engine. There is another one which pushes and publishes into our analytic engine, which is built on top of Redshift. And then we also send some downstream notifications to the services which are integrating with us, like the Kindle services. Now, when the content is available, at the same time, we also start some content processing, especially for videos and for documents. In case of videos, we leverage Amazon Elastic transcoding services to cut some previews and thumbnails. And in case of documents, we create some PDF files such that we can provide preview functionality on any device, especially on mobile and web, to our customers. Now, if you notice, synchronously, we just write the content to S3 and the metadata into Dynamo. And this helps us to keep low latencies, and we leverage the scaling and the durability of both S3 and Dynamo to further scale our customers. And everything else is done asynchronously, like the populating the indexing engine or processing the content as well. So this is a key design pattern which we leverage to scale, and at the same time process the metadata and the content and provide the near real-time experience which our customers are looking for. This loosely coupled architecture also helps to build more fault tolerance. Like if there is an issue with our indexing engine, it doesn't really hinder the upload of file here. Now, when a customer requests to download a file, say in this case, let's take a case of maybe they want to download a photo from their mobile device. In that case, the app will hit our service. We will go get the metadata from Dynamo, get the content from S3. If this image is really a huge image, then we cut the preview of the image into a proper device-friendly format, and we also cache that preview of that image. So smartly caching on the download path helps us to scale on all the download requests. So overall, we rely heavily on Dynamo and S3 for scaling, performance, and durability. And then we do all the other processing asynchronously, which helps us to achieve the goals I mentioned earlier. At this point, I would like Kevin to come over and share with you how we leverage S3, what were some of the challenges we faced, and where we have to do something more custom. Thank you.
I need that. There we go. Thanks, Tarlochan. So how do we use S3 in Cloud Drive? As Tarlochan has mentioned, it is the storage, it is the persistence engine for our customer content, and we have a lot of customer content, but we don't do a whole lot that's very special as far as how we use S3 to store that data. We also generate quite a bit of derived content. So for example, when you upload a video, it might not be in a format that's playable on all of the mobile devices that you want to view it on, so we will transcode that video. When you upload a document, similarly, if it's a Word document and you want to view it on your phone, we'll transcode it or translate it into a PDF format so that you can at least view it on all kinds of mobile devices. So we have a lot of derived content. Most of that goes into S3 as well, and I'll give you more details for both of those categories of how we do that. We generate a lot of log files because we have a lot of servers running, and I'll talk about one particular path that we use that involves S3 for processing log files and getting useful data out of them. We also use S3 for some areas that might not immediately come to mind, but we've found it's a very quick win for us, such as for coordinating changes to dynamic configuration across our fleet. I'll talk about that. We back up, our metadata is equally important to us as our content. If we were to lose the metadata, we wouldn't know where to find the content. So we're pretty religious about backing up our DynamoDB tables in case we ever needed to do a disaster recovery operation. But we also find that that's useful when we need to do things that would involve a table scan on our production table. When we have the Dynamo backups in S3, we can operate on those instead and figure out, for example, for a backfill operation, what files we need to operate on without affecting the running production system. And all of this S3 interaction that we do using the regular Amazon AWS SDK. Our services are primarily written in Java, so there's no backdoors that as an Amazon team we have into S3 that you all don't have. We use the standard consumer S3 service through the standard SDK, with one exception that I'll talk about. So customer content. We use the standard S3 storage options, no reduced redundancy storage. We don't use Glacier. All of our customer content, when you upload a file, it goes into a single bucket per region, which means that we have a lot of objects in a single bucket. And that's okay, because S3 has essentially no limit on the number of objects that you can store in an S3 bucket. Where it does have limitations is on operations that involve similar key prefixes. So in order to support listing objects out of a bucket by key prefix and some of the other operations that S3 has, it has to partition keys by key prefix. And if you structure your keys in such a way that a particular prefix is being hit harder than the others, you can run into performance problems. So in order to avoid that, what we do is generate a random key, so there should be a completely even spread of operations across all of the prefixes of our billions of objects in our content bucket. We store that randomly generated key in DynamoDB, and so we have to go to DynamoDB anytime we want to download content in order to find out where it is in our content bucket. That means that list operations essentially are not much use for us, but that's a price we're willing to pay. We also use the S3 server-side encryption option for all of our content. So all the files that you upload to Cloud Drive are encrypted at rest, and they are also encrypted on the move because we use SSL or TLS between all of our various services. We generate a lot of log files, as I mentioned. At the moment, we've got over 800 servers running across our 3 regions. We'll go well over 1,000 at our peak time of year. Interestingly, our peak time of year is different from the rest of Amazon. For the rest of the company, it tends to be the Christmas buying season. For us, it's the Christmas gift opening season. So it's Christmas morning when people unwrap their new Kindles and their Fire TVs and things like that, and hook them up to their Prime accounts and start to import images from Facebook and whatnot. That is where we see our annual peak of service load. So at the moment, I'm not talking about peak, but at the moment we're generating over 200 gigabytes of log files an hour, and we deliver those to an internal Amazon service, a very simple web service called Timber, and Timber archives those for us. It encrypts them first, it archives them in S3 and keeps track of them and gives us various ways of locating those files and accessing them. So I'm going to talk about what we do with those well, first I want to talk about types of log files, so that you'll understand what I mean when I say service logs. So we have normal application logs, just like I'm sure your applications do. The application writes out a message, it gets time-stamped, severity tagged, and that's very useful for debugging individual service failures. It's not very useful for understanding the overall performance of our system. For that, we rely very heavily on service logs. And service logs follow a standard format across all of Amazon. It's one record per service invocation, and we write a lot of timing information and counters in there, and that's where all of our metrics come from. Service logs feed into our service dashboard so we can watch the real-time health of our system, and then we archive them off in Timber along with our other log files. We also save some wire logs. Those quickly become so big as to be of limited use. We don't save off any web access logs, for example, and so other forms. It's primarily application logs and service logs for us. So here's one of the things that we do with our service logs. On an hourly basis, Each of our servers is writing those logs to Timber. Timber is encrypting them and storing them in S3. We have a Hadoop cluster that is managed by Amazon EMR, Elastic MapReduce. And for every hour's worth of logs, we kick off a job on our Hadoop cluster, which queries Timber to find out where that hour's worth of logs are, downloads them, decrypts them, and transforms them into a Redshift load file. The load file then gets uploaded back into S3. It's encrypted again. And then we use Redshift's capability to, on a massively parallel basis, to suck that data into our data warehouse. And then that's the basis for our regular reporting and our ad hoc analytics. I mentioned that we use S3 in a way that might not immediately jump to mind, which is for coordinating dynamic configuration. We make heavy use of what are sometimes called feature toggles or feature switches. Ours are actually a little bit more than a switch. When we roll out a new feature, it's almost always behind a feature toggle. And the capabilities that we have include the ability to enable that feature for certain test customers. So we can roll a feature out into production at production scale and production configuration and then test it against our some test accounts that we have. When we're happy with the way that that's working, we can slowly dial up the use of that feature while we watch our system and make sure there's not any unanticipated problems operating it at scale. So we'll start it off at 1% and gradually climb up to 100%. We do this with configuration files that we store in S3 simply because it's a really easy way to do that. So our servers poll our configuration files on a minute-by-minute basis. They use the HTTP head operation, which is what happens when you call S3's get object metadata operation. And they just remember the last E tag that they saw. And if the E tag changes, they read that file and consume the new configuration. One thing I want to mention about this approach, it works really well for us, but it also leaves you, once you're dialed up to 100% and you're sure you're not going to be rolling that feature back, with a bunch of conditional code in your code base, and you need to set aside cycles to remove that because that just becomes technical debt. So after a while, we pull that conditional code out, we get rid of the config file for that particular feature, and it becomes a baked-in part of our system. So I want to talk now about a few of the design decisions that we've made along the way, or challenges that we've run into, and the solutions that we've come up with for those. And the first one is that we deal with a wide variety of file sizes, and a one-size-fits-all strategy for uploading and processing those files doesn't work very well. We've got everything from text files to virtual machine images. Even within a single category like images, which makes up a big part of our content, there can be 3 orders of magnitude size difference in the sizes of the images. We want to maintain fairly linear performance as best we can across all of those file sizes. And we want to make sure that if a bunch of large uploads happen to hit one of our servers, it doesn't cause resource starvation that adversely affects the other things that that server is doing, like managing downloads and content processing and uploads of smaller files. So in order to do this, our upload logic is size aware. When we get an upload request for a file that's 15 megabytes or smaller, we do the simplest thing possible. We use the S3 put object operation. We upload that file in the request thread, and we do our content processing, we do our metadata updates, and we return status to the client. When we have a larger file that's being uploaded, or when we don't know what the size of the file is, we switch over and use the Amazon S3 multi-part API. So in that case, in order to manage in order to prevent resource starvation, we have a thread pool that's dedicated to doing the multi-part uploads. In front of that thread pool, we have a blocking array. So when a particular machine gets overloaded with large file uploads, what happens is the thread pool gets consumed, the blocking array gets filled up, and we start to reject requests for new large file uploads. And then that propagates back to the client, who can retry and hit another server that's not having that resource problem. We are currently uploading using the multi-part API with a fixed 5 megabyte part size. If you know a lot about multi-part, then you'll realize that that implies a limitation on the file size that we can handle because you can only have 10,000 parts in an S3 multi-part upload. And so that means that we currently have a 50 gigabyte file size limit. And that's something that has been acceptable to us up to now. Obviously, that's going to change in the future, but it's a fairly easy change for us to make. We just either have to go with a larger fixed size, fixed part size, or a dynamic part size.
Why do you get the starvation? Because the data goes directly into it.
Let me hold the questions until the end where we can get you on the mic, and we'll talk about that. So another aspect of our system is that whenever possible, we like to make the content immediately available. And by available, I don't just mean the ability to download what you just uploaded, but to download thumbnails of it, to search for it and find it and whatnot. So that's a challenge because some of the content processing that we do takes quite a bit of time. So our solution for that is a mix of content processing strategies. We sometimes do synchronous processing, sometimes asynchronous, and sometimes what I'll call optimistic synchronous processing. So let me give you some examples of that. When you upload an image or a video, one of the first things that we do is extract the EXIF metadata from it, and we store that off for indexing and searching and whatnot. That's a pretty quick operation. It, by and large, doesn't depend on the file size because that metadata tends to be up at the front of the file. So we do that synchronously. So when we return a 200 response to you as a result of an upload of a video or an image, all that metadata is available in our metadata store in our indexes. Video transcoding, which we do so that you can see your videos on different devices, is quite different. It depends heavily on the size of the video. And we also don't do that in our own service. We rely on the Amazon Elastic Transcoder service. So that is an asynchronous operation. We store the file off in S3. We send ETS a SQS message, and usually within a matter of a minute or less, they transcode that video into the formats that we request, and we have those available in S3, and we get notified using the simple notification service. Finally, we've got a type of processing that we've added fairly recently as we have upped our game on the way we handle documents, which is to transform documents to PDF. So if you upload a Word document from your desktop, you can at least read it on all of your devices as a PDF file. And we found that the time required to do this is pretty unpredictable. It doesn't just depend on the size of the file. It doesn't just depend on the format of the file. So what we do in an effort to maximize the amount of, to minimize the latency for the availability of this PDF transformation is we try it. We kick off a synchronous operation to do the transformation. If it takes too long, we'll kill that, return a response to the client, and then kick off an asynchronous attempt to do that. Since a lot of our clients are running on mobile devices, a lot of our clients have intermittent network connections. And the initial versions of our API required uploading files in a single HTTP request response. And that's a very difficult thing to do when you've got an intermittent connection or if you have a slow connection. So one of the things that we are rolling out is an ability for clients to resume an upload because, well, let me back up. Earlier versions of our system had a multi-part upload API. That's very similar. In fact, it was kind of a thin layer on top of S3's multi-part API. And in speaking with our clients as we were developing new APIs, one of the things that we heard was that that was a difficult, complex series of operations for them to go through. They've got to maintain a lot of state on the client side about what parts have been uploaded, what parts haven't been uploaded. They've got to notify us when they're done. We end up with a lot of never completed multi-part uploads. It was not an ideal situation for client complexity, particularly for happy path operations. So in an effort to make that a simpler operation for the happy path and still allow recoverability, when we failed. We are providing a resumable upload capability. And the way that this works is that we tell clients, if you want to upload a file, we don't care how big it is, we don't care how small your pipe is to us, or how intermittent the connection is, just go ahead and start to send it to us just like you would for a small file. If it fails midstream, then we save off the information about our ongoing multi-part upload, and we give them a way of coming back to us and saying, how much did you save and where should I resume? And then they can resume the upload just using the standard HTTP content range header. And when we go through as many cycles as we need to, they're making progress on the upload of this file. And whenever we get the last byte, then we can complete the multi-part upload and make the content available. We ran into a problem implementing this that I want to call out to you because it was quite unexpected to us. In fact, we didn't realize this until we first tried to exercise this capability in an environment other than a single developer's desktop. And that is that the S3 multi-part API, which is composed of what I think of as a transaction. You initiate the upload, you upload the parts, and then you complete the upload. That needs to be done with a single IAM principal's credentials. Our service is running on EC2 instances, and we use for all of our other interaction with AWS services, we simply use the instance profile credentials that each of those hosts receives. The thing that we discovered is that doesn't work for multi-part uploads. You can't use instance profile credentials and have a multi-part upload that spans hosts because the principal that's associated with those credentials differs on each of your EC2 hosts. So we talked with the S3 folks about this. It's not a very well-known limitation, frankly, in their API. The URL that I've got on this slide here is to a blog post, an AWS blog post that talks about this a little bit. But talking with the S3 team, they made a couple of suggestions. One was that we could use the security token service to provide credentials for our multi-part uploads, or we could use pre-signed URLs. We went with a STS solution. So the way that this works is that instead of using our instance profile credentials to initiate, upload, and complete the multi-part transaction, which can now, in the resumable world, be happening on multiple machines, we go off to another service that has a consistent set of IAM credentials, and we ask it to generate STS tokens for us, and then we use those tokens for the multi-part uploads. We continue to use instance profile credentials for all of our other AWS service interactions. So like our uploads, our downloads also vary quite a bit in size. And we want to maintain reasonable performance. We have the same kind of resource starvation concerns. When a bunch of large file downloads hit a machine, we don't want it to fall over for the other operations that it's performing. And so we also have size-aware download logic. So if you ask for a download of a fairly small file, and our boundary is currently at 5 megabytes, we go to S3 and do a single get object. Again, we do it the simplest way possible. We do it on the request thread. We do see intermittent failures, network-oriented or network-related intermittent failures, even sitting potentially in the same data center with S3. So we do retry those downloads one time. And this simple approach covers about 90% of our customers' files. For larger files, we have implemented a parallel download capability. Now, this is not something that comes out of the box today in the S3 SDK. You can go out to GitHub and find third-party or open source implementations of parallel download capabilities for S3. We wrote our own using Apache HTTP client. So we download these large files in order to maximize the use of our bandwidth between S3 and our EC2 instances in 5 megabyte chunks using range requests that S3 supports. So we generate an S3 pre-signed URL and hand that off to a dedicated thread pool. And this works a lot like it does for our large file uploads. We have a single thread pool dedicated to this, so we can limit the resources that get consumed. We have a blocking queue in front of it, so if too many large downloads hit one box, those resources get consumed and we can fail back to the client, and other parts of other things that the service is doing are unaffected. This allows us with Apache HTTP client to have a connection pool and to reuse connections, so we save a lot of cycles on the setup and teardown of our connections with S3, because all that these connections are doing is range request downloads. So we've talked a lot about thumbnails, but one of the things that I'm not sure that we've made clear is that for images, most of our thumbnails are generated on the fly. So we do this to keep our service as simple as possible. We don't try to save off thumbnails in S3 or any other storage system and look them up. We get thumbnail requests in various sizes from various clients, so it makes sense for us in most cases to simply cut a thumbnail with exactly the parameters that are requested on request. And that works out well for most images. If you take an image from your cell phone that's a few megabytes in size, it really doesn't cost us that much to download the entire image from S3, cut the thumbnail, and serve it out as a 256 by 256 image. It does cost us a lot, though, when we start talking about larger files. In that case, the expense comes in two areas. We've got a large file to download from S3, and then we've got a large file to cut a thumbnail from. So one of the things that we have added to our system is the use of another S3 bucket, basically as an infinite cache for thumbnails. So when we get a request for a thumbnail from a large image, the first time we'll download that from our content bucket and cut it down to an intermediate size of, I think it's 2K by 2K, and in JPEG format. And then we'll cut that, we'll save that off into a separate bucket that we have where we've applied an expiration policy. So we have a 48-hour expiration policy on this intermediate size thumbnail. We'll cut it down to the final size and deliver the response to the client. The next time that they call asking for that same thumbnail, or a thumbnail based, actually any thumbnail based off of that same image, we'll go off and get the 2K by 2K image from the thumbnail bucket and save about 90% of the download bandwidth from the content bucket. So we do this for any standard image formats that are over about 10 megabyte in size. And we do it for other image formats, which can take quite a while to cut thumbnails from, primarily raw images. So we're caching those in a separate S3 bucket with an expiration policy. And let me mention what our key is, because as I mentioned before, keys, in particular key prefixes, are important. We use a key that's generated from the customer ID, the image ID, and the image version, and then we hash those things. If we didn't hash them, if we just used a concatenation of those things, then a bunch of requests from a single customer could cause us a hotkey problem. So we just generate a cache. And the reason that we've chose those things is that they are enough to uniquely identify an image in S3, and they all come in their thumbnail request, so we don't have to make a trip to DynamoDB in order to pull that metadata out. And the final challenge I want to mention is what we do with large downloads. In previous versions of our system, we did a lot of this actually, where we would generate a pre-signed S3 URL and hand it off to our clients and let them interact and let S3 do the heavy lifting of moving the bytes around. That was a less than ideal situation for us as a service provider, because it didn't give us a lot of visibility into how clients were using our service. We knew when they asked us for an S3 URL, but we didn't know what kind of retries and what kind of failures they were running into. So we made a very conscious decision with the current generation of Cloud Drive to become an intermediary between the content in S3 and our clients in most cases, so we could do things like generate thumbnails on the fly. However, that doesn't work in all situations, and in particular when we have really large files that we're not going to perform any translations on, any transformations on the fly, files that there's no reason for us to write to disk on our servers before sending it back to the client. We will, for compatible clients, generate a pre-signed, short-lived S3 pre-signed URL and just let them go directly to S3 for downloads. So I want to leave you with a few takeaways. One of them is that S3 is a very flexible system. It's such a simple API that it lends itself to a lot of different use cases. So we use it for the obvious things, the big data things like customer content and log files, but we also use it for some things that you might not immediately think of S3 as a candidate for. We use it for as basically an infinitely sized cache with a very simple eviction policy. We use it for coordinating configuration across our hosts. So keep your mind open as you're working with AWS services and rely on the simplicity of S3 to do things that might not immediately jump to mind. The selection of keys is important. I've told you what we do with keys, and if you're going to have high volumes of API operations against S3, it's important that you do the same. Realize that your upload and download strategies can't be one size fits all. Well, it depends on your service, but for us, they can't be one size fits all. So we have to put a little more smarts in the service as far as how it deals with uploading and downloading different kinds of content and different sizes of content. Something I haven't talked a whole lot about is, remember the first fallacy of distributed computing, the network is reliable. The network isn't reliable, and when we look through our log files, we see regular intermittent failures in our interactions with S3 and with all the other services that we talk to as well. And what we have arrived at doing is a single retry, which is going to work in almost all of the cases of intermittent failures, and then simply failing back to the client. The problem with more sophisticated retry policies is that we're just one service in a layer of services, and if every service is doing 5 retries with exponential backoff, you get a multiplicative effect when you have a hard failure, and it takes a long time to return that final failure to the client, who's going to have the final say about retries anyway, and those long-running operations can cause resource starvation problems. So before we learned this lesson, we did see some problems with hard failures causing us to run out of threads, for example, on servers. So keep that in mind and be smart about what your retry policies are. I'm going to hand it back to Tarlochan for some final thoughts.
Thank you, Kevin. So if you haven't already tried Amazon Cloud Drive, try it. Like I mentioned, there's some great subscription plans. You can try it for free for 3 months, and if you're an Amazon Prime subscriber, you get unlimited photos for free. If you have some cool ideas, build some apps leveraging our API and SDK. There's some great revenue sharing opportunities, and you can reach millions of customers. Well, thank you all for coming, and remember to put your evals. Myself and Kevin will be here if you have any questions. Thank you.